All right. Hi, everyone. Welcome to our next seminar. So I'm delighted to introduce Lina Necib, who's coming to us from MIT. Lina is an assistant professor at MIT and has been doing for several years a lot of really interesting work about dark matter and constraining dark matter using observations of the Milky Way. And it seems like that's what we're going to hear about today. So without further ado, I'll pass over to Lina. So thanks a lot, and I'll leave it in your hands.
Thank you so much. And yeah, thank you so much for the invitation. It's great to see you all. And I'm very excited to be telling you about what my group has been doing over the last couple of years in terms of mapping out the dark matter in the Milky Way. So if you went to the Southern Hemisphere, which I guess you guys are all in, so this is a lot less surprising to you than it is to me, you would be able to see in a very, very dark spot. You would be able to see the sky just like this, where it's really beautiful to see the Milky Way itself, the center of the galaxy in the middle right here, but also you would see something like those satellites that we have, like the Large Magellanic Cloud, the LMC, and the SMC around here. However, what I've been trying to look for and what I've been thinking about is really not looking at the galaxy through this, but rather trying to see what the dark matter underneath actually looks like. And that, or at least my own rendition of it, should look something more like this, where there will be an extra density of dark matter at the center of the galaxy, but also around those satellite galaxies that we have. However, if we try to really think about it, dark matter, we don't really know exactly what it looks like. For example, dark matter could be warm, in which case this figure could kind of look a little bit more like this. Or it could be self-interacting, where the density is a little bit more even and the shape of the halos will be a little bit more spherical, or it could be something else altogether. So what we'd like to do is really combine observations to figure out exactly what dark matter is doing underneath. So the goal of my research has been to kind of build these glasses in which we go from the stars, mapping out the stars, to the dark matter. What I've been doing is really doing this is like in 4 different spots around the Milky Way. So I work on trying to understand the phase space distribution of dark matter in the solar neighborhood, as well as trying to find more and more of these solar streams. But really what I'm going to be focused on a lot more in this talk is the most recent results that we've got for the Galactic Center and the Galactic Halo, as well as dwarf galaxies. A question that I get quite often, unfortunately, more often in my department, is what are you? Because it seems what I do combines a lot of different fields. And indeed, so in that case, I just like to tell everybody what I do. And it is really combining a background in astroparticle theory with results from new telescopes. And I will tell you about these 4, at least for today, with some machine learning techniques, galactic dynamics, and cosmological simulations. So it's really trying to blend in a lot of these different tools to have a better understanding of the map of dark matter, and in particular, what is going to tell us about dark matter detection in general. So, of course, I don't do this on my own. I do it with an amazing team that we have. Yeah, my group kind of they voted on a name called, and like we call ourselves the Cosmic Code Breakers, and they did like a whole logo and everything with Gaia, which I find very, very exciting. But in particular, what I would like to highlight is that some of my group members, especially the ones that were left, are doing amazing work, especially in stellar stream. So, for example, Nora Ship, she was a postdoc here in the group, and she started a faculty job at the University of Washington in Seattle. And my former student Tree is now a Sierra Fellow at Northwestern. So we've done a lot of work on this, trying to figure out exactly what the dark matter is doing. But something that I would like to point out is really kind of this connection between the particle physics part and the astro part. And that usually kind of brings in this video from PhD Comics. I don't know if people have seen it, or I'm just like, this dates me to be very old. But basically, the dark matter is a clash of worlds, because for the longest time, particle physicists, and I was one of them, we've been trying to kind of build new Lagrangians and new models that try to figure out what dark matter is at the smallest scales. Separately, and unfortunately very much independently, astrophysicists have been looking at the effect of dark matter, although not too focused on it, in like galaxies and galaxy clusters and how it affects things like rotation curves and a lot of that. But the really important part is that these two worlds are actually very much connected, because the particle physics of dark matter, for example, does relate to the galactic dynamics. So kind of the theme of this talk is going to be really kind of portraying these dichotomy of the particle physicists and the astrophysicists and trying to understand their perspectives of how to kind of build this dark matter map. So today's talk is going to be focused on understanding the map of dark matter in the Halo and towards the Galactic Center, as well as separate work on dwarf galaxies. So let's get started with the Galactic Center. As you would know, if you were to plot the rotational velocity as a function of the distance from the center of a galaxy, you would find that those velocities kind of go up and then go down, or at least that is the expectation, and something that I teach my first year undergrad students in mechanics. However, with the work of Vera Rubin and collaborators, they've actually found that dark matter kind of like the velocity, rotational velocity actually does plateau at some point, and therefore there is something that's missing, and that is the dark matter part. So then you would say, okay, well, Vera Rubin has done this in the 70s. Surely with all the data that we have, we can actually also do the same thing, the same exercise, where we can go from the circular velocity, use that to get the gravitational potential underneath, and from that get the dark matter density, of course, within some assumptions here and there in all of these steps. And the reason that this is interesting is because it tells us about the density profile of dark matter, which is quite critical in understanding what dark matter is. So unfortunately, we still don't know really what the density profile should be. So for example, we know from dark matter only simulations, actually we've known since 1997, that we're expected something to be like NFW, where the inner part grows as r to the -1. However, there are also alternatives in which dark matter is actually ends up being cored, which means the profile is actually flat. So to kind of introduce the lingo that I'll be using, this is going to be a cusp here, the r-1, versus the core, which is r=0. And this is interesting for different people for different reasons. So for example, if we start with a particle physicist, they would care because you'd expect cool dark matter, again with baryons, which we'll discuss later, without the baryons, to be cuspy, or density profile to be kind of really spiky, versus if, for example, dark matter had some kind of self-interaction, that might actually core up the inner profile. So not only is this kind of a lens that tells us about the particle nature of dark matter, but also it kind of helps us understand the dark matter annihilation signals. So for example, if dark matter were to annihilate in the center of the galaxy, it would produce standard model particles, which in a lot of cases, it could be gamma rays, as we've seen, but it could be also electrons, positrons, neutrinos. I think anti-deuterium, you can kind of have so many of these. And basically, what you would want to do in indirect detection searches is see if you can kind of have more of those particles, even neutrinos, that you'd expect over a background. The interesting thing about this is that the signal, especially for annihilation cases, is going to be proportional to the density squared, which means that something like this that is off by a little bit over an order of magnitude can actually have differences of orders of magnitude in signal expectation, which is why this is really critical. If you really didn't care about the particle physics side and you think that we can kind of look at it from the astro side, well, this is still important because it really tells us about galaxy formation. So this paper from the prior collaboration back in 2020 looks at the inner profile right here within a certain definition as a function of the stellar mass, well, the inverse of the mass to light ratio. But basically, you can think of it as this is the smallest galaxies, the classical dwarfs, a little bit bigger, bright dwarfs, and the Milky Way galaxies. And what you see here is that if you were to look at the dark matter only, so these open circles, then the inner profile is expected to be cuspy, just like this black line. However, if you were to take into account baryonic effects, different groups will find it in different ways, of course, but in particular, you would see that there is like this bump at a particular mass, that of the LMC. So the LMC is going to be a little bit more cored, and then the efficiency of making cores actually goes down as you go high at masses. So this is interesting to really understand, which means that if we see these cusp and core, for example, for the Milky Way versus like for other galaxies, it really will help us figure out exactly how galaxies form. And of course, it will help us understand baryonic feedback, which is very interesting in the recipe of forming galaxies and also in disentangling with dark matter. So let's go back to this. We talked about rotation curves briefly, and again, Rubin did it in the 70s. How hard could it be? Famous last words. So what my group and I wanted to do is actually build the circular velocity or the rotation curve of the Milky Way itself. It's a little bit trickier than it is for building a rotation curve where you're living inside it versus looking at it from the outside, but we're going to try that. So for that, we need really three components or three kind of things that we need to add. So velocities, distances, and how you model everything. So let's start with the velocities. And basically, we have a machine that does that. Well, at least we had, because now it's shut down, unfortunately. But basically, the Gaia Space Mission is a mission that was launched in December 2013 with the goal of providing us with proper motions and parallaxes of so many stars. And indeed, it has delivered up to Gaia DR3. So we've got positions of proper motion, so basically 5D kinematics of about 1.5 billion stars, a subset of which of 33 million stars will already have radial velocities or line of sight velocities, so 6D kinematics. Gaia DR4 is going to be coming towards the second half of next year in 2026, and is going to bring that 33 million number, I think, by at least like another by another factor of 3 to 4. The other thing that we need, so velocities, we got that down, or at least Gaia got us covered. The next thing that we need to do is distances, and we need accurate distances. So here on the right, you see that the extent, at least, of Gaia to have measuring uncertainty distances with an accuracy of 10% is about 10 kiloparsec away from the sun. Eventually, and these are just for measurements of proper motion. This tiny little circle here is not just to tell you where the sun is, but really to show you the extent of the previous mission, Hipparchus, that ran from 89 to 93. And to get distances accurate to 10%, it was just basically up to 100 parsec. So it's interesting to go from hundreds of thousands of stars to all the way to over a billion stars, which is quite incredible. However, although it's very, very powerful, the distance measurements or the parallax measurements actually do degrade the further you go. And we need a little bit further than 10 kiloparsec. So to kind of deal with this little bit of a problem, we try to figure out a better way to measure distances. And we use a data-driven model to actually compute such distances. For that, we use this telescope from the ground, so apogee. Apogee is basically a spectroscopic telescope. It gives me something like this, stuff that I don't understand because I always had somebody else reduce data, which is great. However, we can use these spectra or these fluxes to measure what we call the new spectrophotometric parallaxes. So basically what we do is we take the flux across all of these wavelengths, as well from apogee, which is a high resolution, which provides us with high resolution spectra, along with photometry from WISE and Gaia. And we tried to kind of put this into a model where we predict the coefficients to correct the parallaxes that Gaia is measuring. And indeed, it does work actually pretty well. The unfortunate thing, of course, is that it comes at a cost. And the cost is that we go from that 33 million stars that Gaia has down to 33,000 stars because we're using the high resolution spectrum from apogee. Actually, the initial one is 100,000, and then you kind of do some cuts and you go down to 33,000. Either way, we do lose a factor of 1,000 just because we're looking for these high, well-measured spectra. But 33,000 is still great, so we can definitely make do with that. So the last part that we do is try to model, and this is where kind of things get a little bit challenging, but it's doable. So this is the work that was led by my student, Xiaowei O, who's graduating actually in a couple months. And he is trying to kind of construct the Milky Way circular velocity. So to do that, this is basically what our data points look like. So you can see here in red, they do have statistical error bars on them, but very, very small. The ones in the background gray are the points made by my colleague, Christina Eilers, back in 2019. And you can see that although the error bars don't really change much here because they're so small, we do have quite a bit of an improvement at higher distances. So if you take a look at this, or at least if you have what I call astro eyes, like if you have an astro PhD, which I don't, you would be able to see that this data actually is declining. The thing is, I have a PhD in particle physics, so which means that I need to fit it to be able to see that. But basically, if you try to fit this circular velocity within assuming the Jeans equation and all and the baryonic component from some very well kind of calibrated parameters, what you would see is that the data is actually falling, right? And this is really surprising because Vera Rubin has taught us that it's not supposed to be falling, it's actually supposed to be flat. So if you were to actually translate this to a density profile, it would look something like this, which is where the generalized NFW function is trying to fall really, really fast. And because of this is mainly parametric. So because of the parametric functional form, this is kind of pulling this down as well. And that's why kind of it's making things a lot more chord just because it's trying to pull this at the end, like the higher end, very fast. So you can see that already the kind of this smells like trouble, and indeed it does, because if you were to compile like the enclosed mass of the Milky Way as a function of distance, and you look within the range that we were seeing, which is this, our results are okay, and they're still consistent with other measurements, but you can kind of guess how if you extrapolate and you have the circular velocity actually dropping down, then you're going to end up in extreme tension with all the other measurements. Like this just does not make sense. So we knew that something was up, and we really wanted to understand what was going on. So for that, we tried to kind of go back and review the assumptions that we made. And in particular, we wanted to review kind of, I'm going to put them in three big categories, which is the observational selection function. Basically, did we pick some stars over others that are going to kind of change the expected rotational velocity? The axisymmetry, or how symmetric is our galaxy, and is the galaxy indeed in dynamical equilibrium? So the first question when we're looking about observational selection function is Gaia picking some stars over others? And of course, you might say that it's not just Gaia, right? Because we are going to have the selection function from apogee as well. And I'll go back to that in a second. So to really address whether or not Gaia is picking some stars over others, led by both my students, Xiaowei and Tri Nguyen, we actually build these synthetic surveys of Gaia DR3 based on the simulated fire galaxies. So we have these cosmological hydrodynamic simulations from the fire collaboration. And we took 3 of these galaxies and produced synthetic Gaia DR3 surveys, which means just answering the question of what would Gaia see if we lived like that, if we lived in some of these simulated galaxies. And these are, of course, publicly available for everybody to kind of use and play with. And we applied our entire pipeline on these synthetic surveys. And what we found is that actually the synthetic surveys, at least from the Gaia selection function, did not really have much of an effect on the observed rotation curve. The interesting thing, of course, is that it's not just Gaia, it's also apogee, and apogee selection function is kind of tough to build. But we tried to make some selection in which we looked at very specific stars, so basically bright giants, which is what apogee would see, and there wasn't any distinguishable difference that would actually change or affect the velocities, at least definitely at those distances. So we think that the observational selection function is actually okay. Next, we want to discuss the axisymmetry. So for that, we took our synthetic surveys and we looked at, well, right now I'm simplifying the picture. I'll look at two spots, but we actually looked at different, I think, 10 different kind of corners or wedges of the galaxy and reread the same thing and tried to compare what is the recovered circular velocity that you would get. And indeed, this is not a good assumption because the galaxies that we had and that we had synthetic surveys for showed actually quite a bit of axisymmetry. And indeed, we don't really expect the Milky Way to be that axisymmetric. It's just, well, there is first like the effect of the LMC pulling it on one end, Sagittarius has smashed into it. We've seen all of these new structures with Gaia. So there is a lot there. And of course, we're going to go back with dynamical equilibrium. And is the galaxy, has the galaxy had an insanely strong big merger? No, or at least nothing very, very recent, but we know that it has had quite a bit of these kind of dynamical events. So the fact that we assume that it is in dynamical equilibrium and get rid of like these higher order kind of components in the Jeans equation is probably not the best assumption. So this is kind of just like kind of bringing a lot of bad news. So, okay, if we go back to all of this and try to quantify our systematics. So right now I do have the statistical errors as these small error bars, and the systematics are this like pink big region right here. The two fits that I have are one is from the NFW, the one is the generalized NFW, which is here, and one is the INOSTO. So kind of, they can be kind of proxies for core and cusp a little bit. If we take into account like the systematics that we saw in our synthetic surveys, we actually found that they should look a lot more like this. So the actual systematic are much, much larger, and they have been underestimated in the literature quite a bit, just because the field itself had been statistics limited for so long that we didn't really bother kind of trying to understand the systematics that we have. We are in a luxury with Gaia and Apogee and all the other data that we have such low statistical uncertainties that doing this with, we really need to understand our systematics. So this kind of, and also like this paper actually is going to be posted next week. We're waiting for collaboration approval. But basically, this kind of tells us that we're going to go from this old fit, where it's really trying to kind of core everything just so it drops down, to something a lot less inconsistent, where things kind of move a lot more into the direction of a more generalized NFW. Okay, so all of this is really telling us that, yeah, we have a better fit. That's true. We're not really in tension anymore. We're not kind of predicting such a small mass for the Milky Way. Everything is okay. But it still really needs to tell us about dark matter, which we really haven't solved yet. And we've been talking really about this core cusp and all of that. So we need to fix this particular aspect. How do we do that? Really, what I wanted to disentangle is like the core from cusp, like these two different lines. And what I really want is that, as you can see, like when they're out here, they're very much kind of on top of each other, or at least like in this part. Maybe towards the end, they kind of diverge a little. But it's really the inner part that is going to be key in trying to help us understand the Milky Way itself and understand whether or not do we live in a core and a cusp, what's going on there. And although I only took one astro class in my life, I learned that if there's anything bad, it's usually you should blame the dust on it. So here there is a lot of dust in the inner galaxy. That's why it's hard for Gaia to see through, because Gaia's in the optical. So what we want, and if we keep going with this kind of glasses analogy, basically, then what we want is a see-through dust glasses. And for that, thankfully, we have a few $1 billion actually see-through glasses, dust see-through dust glasses, which is called JWST. So if we wanted to zoom in here, actually, can we do this in finite time? And the answer is yes. So I have recently submitted this JWST proposal, so fingers crossed it gets funded. But basically, if we take multiple observations of these stars around here over multiple epochs, basically something that was already measured in cycle 1, and if we measure it every 6 months, just so we can calculate the proper motion correctly, then we should be able to at least reduce some of the error here to try to disentangle these two lines here from each other. Of course, yes, question.
So, two questions really. So, do you think, so first of all, it looks like it's a sharp cutoff. Is there a reason why you have a sharp cutoff at somewhere around 6 kiloparsecs or something?
6 kiloparsec here, you mean?
Yeah.
Oh, yes. So yes, I was about to address these caveats. So basically, technically, we do have data here a little bit. We have, I think, data kind of going into almost like 4 kiloparsec. It's not as many, it's not as good, but we have some. And the reason that we do have this cutoff is because actually the modeling, we know things kind of the modeling needs to be updated. The data is poorer just because you start kind of getting through the center of the galaxy and you have like a little bit of crowding. But also you need to model, for example, like the bar or the bulge a little bit because you're kind of getting into that territory, which is another thing that I was going to just
And
touch
the
on.
second one is, do you think LSST will help in that region?
That's a great question. With LSST, the thing is that we're going to do just like it's still going to be a ground mission. It's not going to be great. The other experiment that actually has enough precision, though, it's not going to be LSST, but rather the VLT and gravity. So what we want, so yeah, my group and I are actually kind of preparing a proposal that is due in mid-March for the VLT because it actually has high resolution. It's in the infrared, or at least like in the atmospheric gap. So we might be able to do this even better than we would do with JWST. Although JWST kind of gives us the fact that it's from space, but yeah.
And so the related is, do you think that the systematics will shrink or
A great question. So the systematics are not going to shrink.
okay.
The reason that I'm advocating for this now is because we need multi-epoch kind of data gathering, right? So we have good proper motion. So we need to start getting that data, which we don't have in a lot of different places, just because most people kind of have focused really on, the inner few parsec to study Sagittarius A star, and then we kind of look a little bit further, but the kind of like the whole dynamics inside is a little bit of a mess. So at the same time, what I was going to say is that we need to start collecting the data, which will take at least a couple of years to give us something tangible and that is actually useful. And in the meantime, we do need to improve our modeling techniques. And one of the modeling techniques that we're actually kind of playing with right now is based on machine learning techniques and how to train on data and try to extract the density field of dark matter instead of kind of doing it like this in terms of like 1D circular velocity where you kind of project everything and mess everything up. Does that make sense?
That's cool. Thanks. Yeah.
Thanks. Great. So yeah, so as I was saying, hopefully we need to start like this observing kind of program or observing campaign to really get those results started. Okay. So in the meantime, what we can do is try to kind of put on theory glasses and try to figure out, is there kind of what is the systematic kind of range of possibilities for the inner galaxy? At least that would be quite helpful for indirect detection of dark matter. So for that, we're going to be using the FIRE simulation. So I'm part of the FIRE collaboration, and in which we actually provide zoom-in simulations of Milky Way-like galaxies. So this is one of our galaxies where we kind of track these galaxies from early redshift all the way down to present day. We have about 13 of these, high resolution based on the Fire 2 physics. And of course, the interesting thing that I love about these videos is that it shows us that how mergers really are such a critical part in galaxy formation. You can see that with the star light, most of it comes like through a lot of these collisions, and you see some stellar streams even. And at the end of the day, things will settle into a disk-like galaxy that kind of looks like the Milky Way. So with these high resolution cosmological simulations, we're actually able to do a lot of this analysis and have a better understanding of the inner profile. So in work that we posted 3 weeks ago, led by my student Abdulaziz Hussein, we tried to understand what is the expected density profile. So for that, you're going to see my amazing PowerPoint skills here. So if we imagine these black stars are dark matter, this is the gas. And on the left here, we have the potential well of the Milky Way. So as the gas radiates, is going to kind of condense and kind of fall into the inner part of the profile. It's going to cool down and turn into stars. This will deepen the potential, and it will kind of pull some of the dark matter with it, which will deepen the potential itself even more. Some of these stars are going to turn supernova, as you can see here, very well illustrated. And that is going to sharpen up like this kind of the opposite effect of the potential. So the first few parts, what I was talking about, is called adiabatic contraction. So we can kind of theoretically think about adiabatic contraction itself. And in particular, what we did in this paper that we posted in January was look at 4 different suites of simulations and try to see how well does this prescription of adiabatic contraction actually agree with what they've seen. So the 4 simulations that we have is Auriga, Fire 2, Vintica-10, and TNG 50. And each of them, we take 6 galaxies. That's why there is a band, just kind of to show the galaxy variation here. And what we did is to take the ratio of what we would expect from theoretically kind of the theory of adiabatic contraction divided by the actual observed hydro simulation. So you would get 1 if basically adiabatic contraction is what you would expect to get. You can see here that 3 of those sets of simulations, so Auriga, Vintica-10, and TNG, are actually kind of very close or consistent, more or less, with 1, telling us that adiabatic contraction, of course, it's not perfect, but it's very close to be an accurate description of the density profile. Fire 2, however, kind of shoots all the way up, which means that the density profile is much, much lower, as you can see here already, that things are getting a little bit cored. And this is telling us that just Fire 2 has such a strong feedback prescription that's really breaking the adiabatic contraction model. So adiabatic contraction is just everything kind of like smoothly, contracting adiabatically, basically. And this kind of gets broken every time you get the supernova and you're ejecting a lot of stuff out. So Fire 2, as its own prescription, it actually is a little bit different from the other 3, or even though each one of them actually has its own subgrid model, but it ends up with a very strong feedback. So what we use from this information is that we can actually quantify our ignorance by setting a systematic band for the Milky Way. So we take, and I want to emphasize that this is for the Milky Way itself. We take the observed stellar distribution for the Milky Way, apply this adiabatic contraction model, which is what you would expect, and you would end up actually in this blue hashed line right here. Then, if you assume this SBF, a strong feedback model, strong feedback model from the Fire 2 and do the same thing, you would end up with this more forward process. So you would be on this end right here. So these 2 lines that we have are actually the density profile that we got from that I presented earlier from Xiaowei, which is really, really cored, although that kind of gets fixed with a new iteration, as well as another one from another circular velocity paper. And comparing this with different profiles that have been used in the literature in the past for indirect detection, we see that some of them are actually quite common and are indeed within this band that we are kind of trying to provide to the community to be able to, like, for use here. But for example, a very big core, a large core, generalized NFW with gamma equals 0 is really not the right description here. And it would be very much, basically, you need really, like, ridiculously strong feedback to pull it down all the way down. And this is, of course, assuming CDM, which means that if you actually end up observing this, it's probably there is some alternative dark matter model that is at play. So putting everything into perspective, we have like this theory prediction here. This is a little bit different from the core NFW, it's generalized NFW, but it's actually with the updated fit that we're going to post hopefully next week. It does end up kind of fitting in quite well. That this is kind of the largest new model that we have. So the point that I wanted to kind of discuss here is that we really need to have a better understanding of the inner galaxy. And at least like I've heard it from the particle physics side is that these are all astrophysical uncertainties that we don't really know. But I think we kind of finally got to the point where we actually do have the resources and the data to really tackle this problem. We just need to, well, we need to get the data, or at least we have the telescopes. We need to get the data, do it. And we also need to build better models and really address this problem. Great. Are there any questions before I move on to dwarf galaxies?
Lina, I did have one.
Sure.
So you showed a plot earlier on. So I mean, it was very interesting to see that most recent one with the, just how much certain of those profiles are in tension with what you see.
Yeah.
You showed a plot earlier where you've got differences with inasto and GNFW
Yes.
functions. So I guess speaking as a particle physicist who's not an astrophysicist, I don't understand how much the difference between those is assumed physical processes or physical settings, and how much of it is pure fitting function. Because the reason I ask this is the following. To the extent that you have tension, you have it out here where your data is getting sparse, and out here where you in this study don't have data. And the potential extra data in the future that you described is all in here.
Yeah.
And so if these differences, which are basically all extrapolation to do with these fit functions, if these differences are due to underlying physical processes, then yes, maybe new data from in here casts light on what's happening out here. But to the extent that they're just about functional forms, then why do I care? Because if they're just about functional forms, then what you learn from the core of the galaxy is not necessarily helping you all the way out here, which is a very different place. Is that you see the question?
Absolutely, yes. And it's something that we actually thought about. The first time that we did this, and we do comment on it in that paper, that the fact that there is an issue with the fitting function. And that's why I was saying earlier that like the generalized NFW is trying to kind of pull it down on the high end, and that's why it's coring it on the low end. This is just a pure fitting function issue. Absolutely. So then why do we care? That's a great question. So I think the reason that I kind of went into all of this about the future data right here is that at least for particle physics, what we really want is to understand the inner data, like the inner galaxy, right? I mean, what happens on the outer end is not really going to affect very much about different dark matter models. So the way initially, before we thought about this kind of going into the inner galaxy, our new follow-up papers were going to be making a flexible fitting function where it kind of basically a broken power law, so you don't have to be extrapolating and looking just within where you see. And the other thing that we were thinking about was, the fitting function. We did have another solution that I don't remember because I'm blanking. But I think, and we're doing kind of completely different new method, ML-based method where we ditch axis symmetry. But the thing is, this kind of got us back to, okay, why are we doing this? Oh, yes. And the second method that we were going to do is actually do a global fit in which we combine data from here with dwarf galaxy measurements and stellar measurements all the way up there. And then that way you can kind of like have something coherent where you have different probes at different distances, right? That will give you a good kind of at least mass estimate for the Milky Way where you actually do have data at different distances and everything is working fine, of course, with the if you update your fitting function. The thing is, the reason that we kind of switched gears a little bit is realizing that, okay, I mean, it is an interesting question to kind of really combine like this data at different scales, but what we wanted to do, at least from the dark matter perspective, is really see what's inside here. And I agree with you. The reason that, for example, I'm not going to go from here and then try to combine it with the dwarfs to figure out the difference between this is going to be because this is going to tell me more about like the fitting function than it is going to be tell me about the inner galaxy, which is really where the whole science is. So that's kind of like the way that I'm approaching it. Did I answer your question?
So what I understood from that was that while what's happening beyond 30 kiloparsecs is an issue and you'd like to see it resolved further, this inner galaxy data is not going to do it, but that's okay because the inner galaxy material has its own interest. And that's fine with me, but I just want to understand that, yeah, okay, so if that's how you view it, then that makes sense in terms of your presentation.
Right. So for example, this one. So yeah, there is data just like for different sources on the app here. And again, if you're doing more kind of galaxy formation stuff, what you would want is really a global fit combination. It's just not what we're doing. But yes, it is.
I'm happy for you to move on. I'm aware the time is passing.
Yeah. Awesome. Okay, thank you so much for the question. So yeah, let's move on and talk about dwarf galaxies. So dwarf galaxies are the opposite regime here. So if you're an astrophysicist, you would expect that things are going to be very much cuspy. And indeed, if there is any variation of that, it means that we really don't understand how galaxies form, which is absolutely critical. The other thing, though, from a particle physics perspective, is that if we're kind of playing the same indirect detection game, but also the other thing that here is that very much with cold dark matter, you expect it to be cuspy, which means that if you get cores or you get something else, then definitely it's dark matter doing it. You don't have to go through like the baryonic gymnastics. So early works have shown that at least some dwarf galaxies might actually have cores. As you can see here, where this is a circular velocity curve of one of these galaxies, and it does fit a little bit better with a core versus a cusp. This is interesting, of course. And then the other thing that I wanted to actually define, because I'm going to talk about it later, is Vmax. So the maximum rotational velocity of this galaxy is just, we call it Vmax, and I'll get back to that later. The thing is, there are a lot of complications in the way that we do this. In particular, we have to assume, for example, like a certain anisotropy function, we have to assume equilibrium, and we have to worry about binaries, especially in the smallest of galaxies, and assume that everything is spherical, etc. So there is a lot that goes on here. So in a paper that I did with a student, Laura Cheng, back in 2020, what we wanted to do is try to kind of go through the standard method in the best of cases, which means that we generated fake spherical equilibrated galaxies. There was nothing wrong with them at all. But we wanted to look at how well did we recover the inner profile, like the density profile originally, with different number of stars. And the reason that we're doing this is because actually a lot of the galaxies that we're looking at have very, very few points. And you can see here on the left that we have the density profile as a function of distance, where the true density profile is this dashed black line right here. And you can see that with 20 or 100 stars, it's actually not enough in this massive galaxy to recover the true profile, especially you end up being posterior driven. If you do this exercise and you also include another thing, which is the measurement errors, and you're trying to fit this generalized NFW, in which gamma here is like the inner profile again. So gamma equals 0 is going to give you a core, and gamma equals 1, minus 1, is going to give you a cusp. You see here that for a 10 to the 9 galaxy, with no errors whatsoever, you're going to end up with a posterior distribution for the truth is the gamma equals 0. So with 20 stars, it's just flat, 100, 1,000. With 10,000, you can kind of disentangle the gamma equals 0 from gamma equals 1. However, and with higher measurement uncertainties, this still works with 10,000 stars, which is a lot more stars than we actually have right now. This gets worse for smaller galaxies like a 10 to the 7 because the velocity dispersion of such system is so much smaller. It's going to be of the order of this 5 kilometers a second error. So things are just going to be all over the place. So for your ultra-faint, even with 10,000 stars, you really need perfect measurement. Otherwise, things are just complete nonsense. So what we wanted to do is build a method where we can get the correct inner density of the dark matter profile. However, the genes analysis, which is the standard method that we use, makes a lot of assumptions to deal with this problem. And in particular, kind of the anisotropy and the equilibrium and etc. And that's why to kind of compensate for it, you need a lot of statistics to get the right answer. So what we did is actually use simulation-based inference and graph neural networks to train a model that obtains a density profile of dwarfs. So the way that we did this is basically train a network on a lot of simulations to figure out, to be able to extract the density profiles. This is kind of a multiple step process, but very, very big overview. We generated idealized simulations. So basically these are distribution function simulations. So it's not really a simulation, it's kind of a realization where you kind of have a potential and then you generate stars that are going to obey this potential and they're in equilibrium. We generate these idealized simulations with different inner profiles, so different gammas. And then we build a graph that establishes the relationships between the stars. So basically it's telling us that nearby stars are going to be feeling more or less the same gravitational potential. We train this network and then apply it to data or to the test simulations. And we use normalizing flow to obtain a posterior distribution. All of this to say is that we kind of did this, and this was led by my former student, Tree Nguyen. And basically, we tried to disentangle a core from a cusp and try to figure out, can we actually do this? So we picked, for example, here in 2 galaxies, and I promise we didn't cherry pick these to make them look particularly bad for genes analysis. But basically, we have a cored galaxy, this is the one in red, and the cuspy galaxy, the one in blue. And we do this kind of genes analysis method, the previous method, and try to disentangle this. And you can see that the posterior distribution actually overlaps, which means that there is some probability for like the cored one to be cuspy, right? And it's harder to disentangle for both. However, with our method, the graph-based method, is actually we are able to disentangle these. And the reason for it is because this neural network method kind of takes into account higher order moments, or like takes into account more of the physics of this and more of the correlations between the stars than the standard genes method. Of course, there are more sophisticated methods than just the genes analysis. So, for example, like the ones that are actually taken into account computationally higher order moments. And we took a look at some of these. So the difference is not as dire as the genes analysis, but the advantage for that is actually that the graph neural network, once trained, can evaluate any galaxy in a fraction of a second versus the other ones that take usually hours or days to get solved. So this looks great, but this was done using idealized simulations or idealized realization. So we kind of generated this very beautiful kind of like sample and tested it on that. So this is not as realistic as we would actually see in real life. So for that, we also wanted to make sure that we understand this a little bit better. So we trained again on these idealized realizations and applied it on the satellites, the mock satellites of the Milky Way. So, or Milky Way like galaxies. The interesting thing about this is that these are hydro simulations where the satellites are a lot more realistic. And in particular, they don't have like this kind of very much entrenched the assumptions of sphericity or a particular anisotropy distribution. And in particular, there are a lot of them that are the ones that are very, very close to the main halo are going to be subject to tides. So it's interesting to see how robust our basically framework is to such things. So we applied this to cold dark matter satellites, and it yields very good fits. So you can see here our method graph MP here in orange. The black is the data points for like the dark matter data points on the inner part. And you can see there are a lot of points in here. I'm saying 100 stars. This is because these are the dark matter particles. And we can do this actually for galaxies that have somewhat few stars, like 86 stars here, and it does still pretty well. So the posterior profile actually that we recover is quite well. It's a lot more constraining than the genes analysis in some cases, especially when you lose statistics. This is not assuming anything about observational errors. So to make sure that we are kind of testing it on both regimes, we did this also with self-interacting dark matter. This one overshoots a little bit, but again, we're doing much better, especially with the very, very small regime of 35 stars. So we're kind of recovering a lot better than genes analysis that kind of gets a little bit lost. And it's also because of the way that binning works. So the other thing that I wanted to focus on is tidal disruption. So I was saying earlier that the satellites that are very close to galaxy are actually end up being tidally disrupted. So if this is the Milky Way itself, and these are your satellites, just because there's a gradient in the gravitational field between the two, you're going to end up stripping the stars in slightly non-trivial ways, and eventually kind of you end up with stellar streams. But in most cases, as a paper that was shown with that was led by my former postdoc Nora Shib, showed that a lot of the satellite galaxies that we actually see today might actually have tidal tails that are a little bit too faint to see. So we wanted to make sure that we are very much robust to that. And indeed, we are. So here what we're plotting is for SIDM versus CDM, we're plotting like the Vmax that we recover versus the truth for the less tidally disrupted and the more tidally disrupted right here. And indeed, things seem to be at least more or less kind of well recovered for Vmax, which I introduced earlier as the maximum circular velocity, and that tells us about the inner gravitational potential. We can do this for M200 or the mass, the total mass, M200. And you can see that this is where things get a little bit out or a little bit tough to recover, especially for the low masses. And this very much makes sense just because M200 is way beyond where the stars are. So you're really extrapolating the density profile all the way out to figure out what is the total mass. And that's why it's very much hard to recover, which is something that is very much expected. But thankfully, at least like for the high enough masses, we're doing pretty well. Again, these tend to be a lot more tidally disrupted anyway. So what we have next, definitely this paper also, so the two papers, the systematics from the circular velocity and this, the paper where we apply this graph MPE method on simulation. Both of them are in collaboration approval until Friday, which means that they will be posted next week. So definitely keep an eye on that. But the next thing in our big pipeline is to apply all of this to actual real data and kind of provide the field with inner profile, density profiles of dark matter in the dwarf galaxies that we have. We have data for dwarf galaxies in the Milky Way and those from Andromeda. So to really summarize, we kind of did a little bit of a tour of the Milky Way, and in particular trying to map out the dark matter using the stars, focusing very much on like the inner profile and the things that would distinguish dark matter itself from dark matter models based on the galactic dynamics. And hopefully we'll keep on going in mapping the dark matter stars from the stars to dark matter. Thank you.
Cool. Thank you very much. Yes, do we have any further questions? So maybe I can start. So I have maybe I have a few things, but people can raise their hand if they want to interrupt me at any point. So yeah, just to let me understand this the reconstruction of the dwarf density profiles, this GNN method.
Mhm.
So you're still assuming that the data you will have is just line of sight velocities. You're not because
Yes.
you're somehow overcoming this sort of mass anisotropy degeneracy, which it seems like you're sort of bypassing the calculation of the Jeans equations entirely because you're not dealing with moments. You're just looking at
Yeah.
star by star. Can you what does the individual stellar data tell you? But there's still you're still only seeing a projection, right, of the velocity distribution. Are you assuming you have maybe some proper motions, or is it? Are they going to be?
So for this method in particular, we're assuming that we don't have proper motion. So we're trying to do this. So everything is getting recovered. Basically, the prior in this method is anything that you actually kind of run as a training set. And for that, we do assume a particular anisotropy profile. And in most cases, actually, the anisotropy profile, like for the fire dwarfs, sometimes it's out of distribution and it still manages to get the inner profile okay. So this is kind of like the interesting part, that it's trying to I do have some figures. Let me see if I can find them quickly. Where we do fit for the inner profile as well. It's just that well, sorry, we fit for the anisotropies, and in some cases it's not very well measured, but all right, come on. There we go. Yeah, let me figure it out. Stop sharing here. And there, here. Okay. You can see the screen?
Yeah.
Yeah. So these are like the beta distributions. So this is a comparison actually with GraphSphere, which is another method that takes into account higher order moments. But yeah, so I think it is figuring things out. Like it's kind of going, we have this OM functional form that's going to go from like pretty much beta equals, well, it can rescale the whole thing.
What's like the ground truth in this case? Did you have is this
the black dots here?
Oh, right. I see. Okay.
Yeah.
But hold on. But but that's like your so those are
The stars. Yes, the stars. It's not dark matter in this case. Yeah.
but then are you assuming an underlying potential? Like is there not like a true kind of curve for what beta R should be? Maybe I misunderstood you.
Oh, No, so basically we're training only on these idealized simulations, which do have like basically a generalized NFW and a particular anisotropy profile. Then we're testing it on fire, where it's just could be anything. And we wanted to make sure that at least our model is flexible enough that it takes into account all of these. And we know, and there have been some papers, for example, about fire, the anisotropy profiles of fire not being kind of the cleanest, or kind of not all of them.
Right, okay, because it's a simulation. It's not a, you know,
Right.
it's not like an idealized potential. Yeah, okay.
Exactly. So this is kind of like well, as realistic as we can get it, where we know already what the answer is, and we wanted to make sure that indeed we do well. And that's what.
Please jump in if you have a question. I can just jump to my next one. Okay.
I would like to ask.
Yeah, go ahead.
So yeah, thanks for the talk. I like my question is more regarding the hydrodynamic simulation. So how sensitive are them to star formation? Because like how well do we know star formation and these kind of processes to get like a consistent outcome of
yeah. That's a great question, and this is why here we use 4 different simulations, just because so the problem with simulation is not just like about well, it's because you're limited by resolution. So at some point you really need to kind of cut things off. And for example, with the Fire 2, just because it's the collaboration that I'm in, so I know that one a little bit better. For example, our star particles are 7,000 solar masses. That's not really a star, right? Like that's a collection of stars, which means that in your code, you have to make some assumptions about the what we call subgrid model or the subscale. And every different simulation actually does this differently. And actually in our paper, my student really insisted on having this appendix that kind of lists all the differences between the different simulations just because he wanted to have it there. And I think it's actually really important. So how well do we know this? It's a work in progress. I think that's why we have different simulations. We don't know it perfectly for sure. And a lot of other of these effects, actually, you kind of have to implement choose a prescription, and then you run the simulation all the way from early times to redshift 0, and then you get what you get, right? A lot of these processes are nonlinear, so it's very hard to kind of tune a simulation just so you can get all the observables correctly, or at least like you try to kind of do the best you can. So for example, we put in by hand the temperature below which like a gas particle turns into a star, or the number density of gas particles to turn into a star, or the energy that is emitted by a supernova. Even you're not tracking a very specific supernova as it ejects everything. Is just you have to make some assumptions, and different simulation sets actually do it differently. And that's why it's interesting to kind of see like the results if you kind of try to quantify this difference. Does that answer your question?
Yes. So, but for example, here in the graph, you are showing like the simulations kind of agree almost, right? Even though they have different assumptions, I guess.
Oh, they have different assumptions. They disagree in the inner profile, which is where the problem is. And actually, just to be a little bit fair, they are rescaled so they match here. But overall, on the outer end, yes, they do get the same profiles for Milky Way-like galaxies. Yeah, we know that well enough.
Okay, thank you.
Is there a specific reason why the fire simulation has a lower density towards the inner?
Yeah, it's because of this very strong feedback. Yeah.
Okay.
Mm-hmm. And that's why we use that to really kind of do the bottom of it. We don't expect if basically fire has, I think, the strongest feedback in any of these simulations. So we would expect the Milky Way not to be worse than that.
Is there a specific physics motivation to choose such a large feedback, or to have that? Or what's the argument?
Oh, yeah, it depends on the different data sets. The different prescriptions. So for example, this is fire, again, we don't tune this one by one. It's just a combination of a lot of different effects that does this. So for example, we do have a code. So this is Fire 2. We do have Fire 3, but the reason that we don't publish papers with Fire 3 just yet is because we still don't understand that kind of feedback prescription on terms of observables and what it did, which actually made quite a bit of changes. So so it's not that it's not a like a small knob that you can change. At least I think some simulations just you can kind of change like just the supernova feedback and everything works out. But for this one, we do have like a kind of try a self-consistent with a lot of different knots all together working together, and that's why we don't change them a lot at a time. Does that? I don't know if that makes sense.
Yeah, no, it makes sense.
I mean, it has interesting consequences. We've got a paper coming very shortly updating CTA constraints on dark matter simplified models and effective field theories. And the fact that the velocity dispersion with the baryonic feedback in the Fire 2 simulations is generically broader, right? I remember the plots in the paper being that the density profile can sort of go up or down a bit, depending on exactly the sort of parameters of the simulation, but the velocity dispersion is always broader. That has interesting repercussions for things like velocity dependent interactions.
Anyone else? Okay, well, I can sort of keep going. There was one thing I just wanted to go back to, which is the rotation curve in a galaxy.
Yeah.
So I mean, the rule of thumb, it's sort of at the textbook level is like, this is sort of don't go there because it's like, the galaxy is quite definitively not axisymmetric in this region, and like you have to deal with the bar. And also like, with JWST, I guess you are seeing through a lot of dust, but I imagine there will still be some amount of extinction, and like to get the circular rotation speed, don't you really want to be in the mid plane to not have to deal with the tilts and stuff above and below. So I don't know, like, to what level of sophistication are you imagining having to go to really extract the rotation curve there, and also more broadly, what does it even really mean? Like, a lot of the stars are not going to be on circular orbits, right, at all. I guess you can still define it's like the gradient of the potential in the radial direction, but like, yeah, it just seems really, really tricky to me. So what are your thoughts on that?
Yes, it is. It is tricky and it's a horrible mess. The way that I'm thinking about it is that I mean, first of all, we need the data eventually. So having it that a few-year program is always good. But I think that even if we go just so I think things are really a mess here. But if we can kind of sort out, at least get some data getting us a little bit closer, it doesn't have to be the inner 1 kiloparsec. Even here at like 4 and 5, which we have some apogee data, and that's why we're going to start playing with the modeling there. I think it's already going to really help because this is where kind of things start to turn, right? Like having I think at a few kiloparsec, narrowing this down is already going to narrow down whatever like systematic band you can think of if you can kind of like really fix things down to 3 kiloparsec out of 3 kiloparsec instead of out of 6. And that will already kind of help, at least in the inner profile of dark matter and indirect detection, just to kind of have a measurement there. And then things can go wild a little bit more, but you have a little bit more of an anchor there. This is what, at least like the first step that I'm thinking of is to make some headway to get inside. After that, yeah, it's going to be a big modeling mess, but we better start it at some point.
Very, very large. I mean, the systematics there will probably be very large, right? I mean, no. I mean, do you expect the systematics there to be small, or the systematics will be very, very large?
Oh, you're asking about the systematics. Yeah, as of now, it's going to be very large, just because we really need to nail down the modeling there of the bar and eventually the bulge. But hopefully it's something that we can work on.
And also then turning that into a density profile, you will also need to know, like when we a dark matter density profile, you would need to know also the gas density and the stellar density, because it's all baryon dominated, right, in that region.
Yes.
So is that well known and enough to then turn this into a density profile?
We have at least like some understanding. Again, I was thinking like on the outer part, it's not so horrible. And the other thing that I'm thinking about is that, yeah, we might honestly also ditch like the whole circular velocity aspect of it if we're really trying like this whole map, density field map. If that works, then that kind of will help with all of this. And everything is going to be a lot more in the training set. So as long as we have very good simulations there, that will bypass a lot of these problems. So yeah, this is kind of like the way that I'm thinking about it.
All right, we're a bit over time, so last chance for any final questions. All right, guess we exhausted all the questions, so I'll stop the recording.